It's the home stretch. We're almost there. There's still some fun to do. Let's get started. Alrighty. So let's see. So there's I've made some updates to the last lecture notes, so you might want to download them. But most importantly, I know everyone is hard at work on their final project. I really ask you to have them in on time. I'm leaving on a jet plane on Tuesday morning. My wallet is calling my. That's interesting. Yeah.
To which states?
Sorry?
To which states?
Where am I going? I'm going to Mexico City. Yeah. Yeah. I guess it's very tough. Yeah, it's very tough. Anyway, I'm giving clothing on Aaron. And anyway, so please, all right, please try. You may not get graded in time if I don't get them. We have to be early on to safety. Very good. Okay. All right. So let's see where we were at, and let's continue on. So we're talking about the problem of spontaneous emission. Okay, and spontaneous emission is a kind of foray into the subject of open quantum systems, which we will develop and discuss in much more detail next semester. So this is a little bit of an introduction to that subject. And what I mean when we think about, we can kind of distinguish thinking about physical systems into two classes of systems. One we call closed quantum systems, where closed quantum systems are one, or just closed systems in general, whether we're talking about this in classical physics or in quantum physics, are ones typically where we have a few degrees of freedom, and we are looking at all of those degrees of freedom, okay? I mean, it's hard for us to even talk about the two-body problem in classical mechanics. It already can become chaotic and hard to model. But nonetheless, when we're thinking about a system where we, in principle, take into account everything, we look at every degree of freedom, then we call that system closed, okay? And a closed quantum system is one where energy is conserved, the total energy of the system is conserved, and in quantum mechanics, the dynamics are described by a Hamiltonian with a unitary time evolution. That time evolution is reversible. I can invert that, and I can take the state at some later time and time reverse it back to the origin. And typically when we have a few degrees of freedom, the motion is oscillatory in some way, okay? And so an example of that is, for example, what we studied previously, where we thought about a two-level atom and a single mode of the electromagnetic field, okay? And that was the James-Cummings model, and it was characterized by, say, oscillatory behavior, where we started the atom in the excited state, and the cavity in the vacuum, and it was a perfect cavity, and there was nothing else going on. We would emit the photon into the cavity, and there would be a kind of coherent Rabi oscillation between these two states, and the population in the excited state would oscillate, okay, depending on the coupling constant, okay. That physical situation is being contrasted with what we're calling an open quantum system. And generally, a general open system is one where we're only taking into account a subsystem, some subset of the degrees of freedom, and we're not taking into account everything. And moreover, it's typical, why we would typically do it, is that the rest of the system includes so many degrees of freedom that we don't have a prayer of accounting for all of them. And so we're typically, looking at just some subsystem. It's coupled to the other degrees of freedom, which we might call the environment. And there can be coupling from the systems to the environment, but we're not taking into account all the other degrees of freedom. And what one finds is that the dynamics then of the subsystem coupled to the environment is no longer described easily by a unitary time evolution. The effect, it's not, of course, if we accounted for everything, it would be unitary, but if we're just looking at a piece of it, it looks non-unitary, okay? And often, especially if we have a large environment, we will have irreversible behavior where some of the degrees of freedom, excitations in the system leak out into the environment and they never come back, okay? And energy will also typically be dissipated in that system. So if we just look at a subsystem. So, we do this all the time in classical physics, right? When we think about, a sliding block, an inclined plane has friction. Where is that friction coming from? Well, there's all the bonds that are being made and broken with the surfaces and all the things that happen in the macroscopic surface, and we're not taking into that account, and so we get a damping motion of the block, in first semester physics. And that physics is true whether we're describing things quantum mechanically or classically. As we discussed, there's some subtleties in the quantum system because of the uncertainty principle and what we saw, for example, we saw one example, if we just willy-nilly put in decay instead of beam splitter, we would violate the uncertainty principle. So we got to be careful, but nonetheless, the basic physics is not that different whether we're talking about classical physics or quantum physics, that the microscopic laws are time reversal invariant. We can't, there's no difference. I can change t to minus t and it's the same. But macroscopically, there's an arrow of time, there's dissipation, there's irreversibility. And exactly how you get that from the microscopic laws is kind of complicated and contentious in some ways and involves hand waving and arguments, and we're going to do some of that today. Okay? All right. So the example we're looking at is spontaneous emission, the phenomenon whereby I start an atom in the excited state. It's not inside this high Q cavity anymore, it's in free space. And what we know is that what will happen is say if this is, there's an excited state, if there's a lower energy level, it will spontaneously decay, okay? This is the first excited state, it will decay to the ground state. And it does so in a manner that's quite different than this. The probability of being excited at a state of time, the probability to be in the excited state as a function of time decays exponentially, right? And this is irreversible. If I started in some superposition of these two, I'd still end up in this state. I'd end up in the ground state with some photon emitted into free space, and I couldn't tell what initial superposition state I had started in. I've lost that information and somehow gone into the environment. Okay? So there's all kinds of things that are interesting associated with this. All right, so the way we're studying this is, our model is we're thinking about a two-level atom coupled to the electromagnetic field, the continuum of modes, in the dipole approximation and the rotating wave approximation, all of which are highly valid. And so we have the atom and the field and their interaction between them in the dipole approximation. okay? This is my two-level atom, this is my field, and then the interaction Hamiltonian. And in the interaction picture, where we allow the operators to evolve according to the free evolution, this is the interaction Hamiltonian, okay? So this problem is like one if you've taken Physics 522, Quantum 2, which is totally incorrect, but anyway, you've studied the problem of time-dependent perturbation theory, right? This is the same idea, where you have the system and it's being weakly perturbed because the dipole interaction is a small interaction compared to the binding energy of the electron to the nuclei. And you typically are looking at rate equations. You're looking at Fermi's rule, and what's the rate at which I go from this? It's a very different picture than we talked about with the Rabi oscillations, right? It's like it was here and now it's there and there's some rate and there's no sort of in between. And that problem is an open quantum. You know, the way we teach Fermi's golden rule, we don't really explain it right as an open quantum systems problem. It's the same one. We're doing this now here in a slightly more, only slightly more sophisticated version than Fermi's golden rule in what's known as the Wigner-Weisskopf theory. It's very closely related. I'll tell you the slight differences, but it's effectively Fermi's golden rule. The only difference between it is that in Fermi's golden rule, you're only looking at the very, very, very early time behavior where you have the thing changes linearly, the population changes linearly as a function of time, and then you look at the time derivative and you get a rate. Here we're looking at more than just the first order, see exponential decay rather than the very early time behavior. But basically, it's the same thing. So you should go back in your minds if you study Fermi's golden rule and think about it again, because that's what we're effectively doing. Okay? So, right. So as we do in time-dependent perturbation theory, we go to the interaction picture because it's convenient, because we see the effects of resonance in the interaction picture. And so in the interaction picture, this is the Schrodinger equation. The state evolves according to the interaction Hamiltonian in the interaction picture. We're starting with this initial condition that we have the atom in the excited state and the field is in the vacuum. And because this Hamiltonian conserves the total excitation number, we are restricted to this subspace of the total Hilbert space. Either we have the excited state in the vacuum or it's in the ground state with one photon in some mode. Okay? This is an infinite dimensional basis because there's an infinite number of modes. Yeah?
How is this an open system if we're accounting for all possible?
Well, it's not yet, actually.
Okay.
It's really not. You know, typically when we're, what would we, it's a very good point. At this point, this is unitary evolution. This is the Schrodinger equation. But we're going to make approximations to treat this as an open system whereby the environment is the vacuum. Okay? So the atom is our system and the environment is the electromagnetic field. Okay? And there's this infinite number of modes into which the thing can leak and thus goes irreversibly, sort of emits into that, and unlike the cavity, never gets re-emitted again. So it's open in the sense that we're going to make approximations due to the fact that this is ultimately going to be an uncountably infinite continuum of modes that will allow us to make approximations that take the truly reversible unitary dynamics to something that is well approximated by this exponential decay. So the system is the atom and the environment is the vacuum. Okay? Right now we're taking into account everything, but then we're going to make approximations that effectively throw away the baby with the bathwater. I'm sorry, baby. All right. Excellent. Okay, so when we did that, then we can write the Schrodinger equation as, say, the state will generally be of this form. It'll be a form that involves amplitudes in the different basis states, and we get coupled ODEs between the probability amplitudes. And when we formally integrated that, we got this integral differential equation. Okay, we eliminated the ground state in front of the excited state, and we get this equation that's not really a differential equation, because the rate of change of this amplitude doesn't depend on what the variable is at the same time. It depends on its whole history from 0 to t. So this is a formal solution, but it's not really a solution at all. I can't really, there's no exact solution to that equation. And that's where the approximations come in, okay? So what we did last time is we said, well, first of all, I'm going to take this guy over here, this sum over mu, the modes, and we're going to turn it into an integral over a density of states, where we have a continuum of mode weighted by a density of states in that volume. That density of states depended on the quantization volume, and that gave us the density of modes, okay? And that became a integral in the spherical coordinates relative to k-space and G only depends on omega sub k, and this became omega squared d omega cubed, and that became an integral d omega times the density of states in a particular solid angle, and then we had this, where this density is omega squared over c cubed times v over 2 pi. So that's the density of states per unit frequency interval in a given solid angle, okay? And we did all of this rigmarole. I'm not going to go through all the algebra again. You can see it on your notes from last time or here. And what we ended up with then was the following. All right, the details of all these factors don't matter so much. I want to get to what we see here, okay? So, at this stage of the problem, we really haven't made any other approximations other than the original dipole approximation and the rotating wave approximation. We've taken the discrete integral over the discrete set of modes and turned it into a continuum integral over a continuum of modes weighted by the density of states. But that's all we've done, okay? And it's at this level, it's still really a closed system description, okay? But now is where, oh wait, I'm missing something here. Right, okay. So now is where we start. What is it? Not really, but it seems like, Henry, we have to be very careful about it, because there's some very subtle approximations like one that do seem contradictory, but they're not. You just have to understand what they mean. So the first thing is here, as we discussed previously, I can think about this whole thing, when I put all these integrals together, as a kind of integral over time, k t minus t prime So, again, this is not an approximation. I just rewrote this in a slightly different way, okay? What does this say? First of all, what is this kernel k function of t minus t prime? It's, well, the limits of integration are a little weird. You can think about what it means when only taking the positive frequencies, but that's really not the key point here. This is the Fourier transform of this, okay? I'll call this thing k tilde of omega sub k, okay? Again, I can think about the electromagnetic field, in this case the vacuum, but we're going to talk in a moment about black body, as a kind of bath in which the atom is bathed, okay? And the bath, the system responds to the bath in some way. The way it responds is by this whole dynamics, okay? And what we see here is a kind of response function. K is kind of a kind of response function. What happens at this time depends on the whole history from 0 to t by some kind of response function. Those of you who know about signals think about response functions. And the question is the response instantaneous, or is it have some delay? So the sort of, to the degree to which, if this thing, so let me maybe come over here. Suppose k tilde of omega or a constant, which it isn't, but let's suppose it were. Then what would this be? It would be kind of a delta. It's kind of a half a delta function because it goes from 0 to infinity to minus infinity. I'll explain that in more detail in a moment. But kind of loosely, this thing is, at least the real part of it is that. It also has an imaginary part. Okay? So what does this mean? What this means is that if I were to look at k as a function of omega, if it were flat, this is k tilde, then this thing, as a function of tau, would be a delta function. Okay? So if we had a completely flat spectrum of that describes somehow the modes of the bath, then we would have a situation where this response function would be a delta function. In fact, let me say it in a slightly different way. Let's say I'm going to call it gamma. Then this would be kappa over 2. I mean, gamma over 2. If that were true, then we get what we want. If it were the case that this were flat, this thing would look like in this situation. We would see that whose solution is that. Yes, sir.
So this kappa characterizes the environment?
It does,
Okay.
because it's characterizing the environment. It's also characterizing the coupling of the system to the environment. So aspects of the environment that are here are, what are the density of states? The environment is the electromagnetic field. So the density of states characterized by, but what is G? G, oh G, where is that? Oh, there it is. G is the dipole interaction between the atom and the field. So this thing that I'm calling K tilde is a function of the environment and the way in which the system is coupled to the environment. Yeah.
So that correspondence that we have there, or constant corresponds to the delta, or roughly.
Yeah.
Is that why, practically speaking, when we're measuring impulse responses, instead of doing an actual impulse, we might sweep it through white noise or something?
Yeah, I mean, from that point of view, yes. From a sort of circuits or signals point of view, yes. But that's a particular example of this. I just wanted to sort of emphasize this fact about if we had this very broad spectrum, and to the degree to which the spectrum was completely flat, then we'd have instantaneous response, okay? If we had something that was very broad with some bandwidth of the bath, then what would this thing look like? Yeah, I mean, it would be another pulse, but what would be its width? 1 over. Roughly. That's what's called Fourier duality, or it's a kind of uncertainty principle, right? The broader the spectrum is here, the more narrow the response, okay? So, what the open quantum system, the way in which we get one of the approximations is to think about the different time scales or frequency scales in the problem. When analyzing any physics problem, the first thing you have to do, what are the scales? What are the characteristic scales in the problem? And what characterizes those scales? So one scale is the bandwidth, the effective bandwidth of the spectrum that describes the environment and the way the system couples to that. That time scale, that I'll call the correlation time, is effectively 1 over the bandwidth. So this time I'm calling the correlation time between the system and the bath. Because, why am I calling it that? Because it's saying what is the width of this pulse or this response function. If it's a delta function, then there's no correlation at all. What happened, it's gone. The system responds instantaneously. Whereas if there is a finite time at which the bath and the system are still correlated and information can come back to the system from the environment and not gone forever, then that's taken into account by the whole history. So the degree to which there is an instantaneous response is the degree to which the correlation time was effectively 0. And it's out the window. That bathwater is gone. I can't get it back anymore. So the degree to which we take this time to be infinitely small is the degree to which this thing has no correlation, it instantaneously goes away, okay? There's another time scaling problem, which is the time scale at which the system changes. In this case, that time scale is 1 over gamma. Okay? And the whole story here is the separation of time scales. So we're interested in systems. We can analyze a system easily if these two time scales are incredibly disparate. We want the case where the correlation time of the system environment is extremely tiny compared to the time scale over which the system changes. Okay? This is the lifetime of the atom. Okay? This corresponds to what we call the Born-Markov approximation. This leads us. So what is important for the Born-Markov approximation? What are the two things? One is that we want weak coupling between system and environment. That, because the system is weak, that makes this small, that makes this big. Okay? Because it's a weak coupling, the amount of the way in which the system is being forced by environment is very weak. That's why this is related to time-dependent perturbation theory. We're treating the interaction Hamiltonian as a weak perturbation to the system, and that means that the system doesn't decay very fast. But there's another part of the Born-Markov approximation, which is the white noise approximation. That is to say, we want this to be huge. Okay? That's the same thing as this statement, just written in the inverse. So the Born-Markov approximation allows for a huge separation of time scales. It says the correlation time with the system with the environment is extremely tiny, and we can take that time essentially as 0. At the same time, compared to this, at the same time, it's a weak interaction, okay? So that separation of timescales allows us to make some approximations to this system, okay? So the first thing we do is we make the Markov approximation. So if we look at this, what does this spectrum look like? We should write out what this is. So G squared omega times the density of states per unit solid angle is something times omega k cubed. It's something times omega k cubed because this thing goes like omega squared, and this thing goes like omega, right? Because we have the density of states over here, with like omega squared. So if I were to look at this k tilde as a function of omega, it would be something that goes off like the cubic. Now, it never really goes up. Eventually, you know, the atom doesn't couple to these high frequencies, at very high frequencies. So there's some cutoff here where eventually the coupling would go small. But this is incredibly broadband. So for all intents and purposes, to the degree to which I can think about this, I can think about this as like white noise. a flat spectrum. And that allows us to make the Markov approximation. And that Markov approximation is the one whereby we can say that this is basically like a delta function. And under that circumstance, I'll write it again. This thing is approximately because what I did is I said, I'm not going to worry about the history from 0 to t because it's instantaneous response. I'm going to replace the t by t prime and bring it outside the integral.
What is omega c again?
Omega c, I'm saying that there's some cutoff.
Oh, I see.
In principle,
Okay.
really the coupling, the G, the dipole coupling to the field can't go up because eventually I'm so far off resonance. But even it went up and up, it doesn't change the basic argument. This cutoff is not so important here. The basic point is that this is effectively flat over the region of interest. Okay, so that's one part of the integral. Now let's do this integral over here. And what do we get? What we get is, let's see, I can bring the omega, I'll call this delta sub k. So I'm going to bring the delta sub k t outside, and then I get the integral from 0 to t dt prime e to the plus I delta k times t prime, which is e to the minus I delta t times e to the I delta t minus 1 over I delta, right? That's that integral. And this thing, I'm going to factor out a t over 2, and then I'm going to get e to the I delta t over 2 minus e to the minus I delta t over 2 divided by 2I delta t over 2 times t. Trick-o-roonies. You may have seen this before. This thing is what?
Sine.
Yeah, it's sine of the thing over the thing, right? So this thing is what's called the sinc function. The sinc of delta times t over 2, where the sinc of x is sine x over x. Okay? Right? So, interesting. So, all right, so what I get then is I get times some phases times the sinc function of omega k minus omega eg t over 2. This thing in parentheses, some phases, I'm not going to worry about them at the moment. Times t. Okay? T times the sinc. Now, let's plot that on top of this, okay? So somewhere here is the resonance frequency. And then we have t times the sinc function. What does this sinc function look like? Do you remember what it looks like? Yeah, that, very good. All right, I'm gonna do that. You ready?
There you go.
It goes up, and then it goes down, and it does that. I'm gonna actually make it more look like this.
It's a delta function with an attitude.
Yeah, anyway, it's got the same zero as everything else, okay?
Is this a different function than what you thought it was? Is this the same function? Just
No, this is not the Fourier transform. What I drew over there was the Fourier transform of this.
Mhm.
This was the sinc function that came from this integral. And they have this is in the frequency domain. That was in the time domain. This is something different. This is about the resonant response, okay? This has nothing to do with the spectrum. The spectrum is here. This is about the response, the thing that we just integrated. Now, this goes up to t, and this thing has a width of what? One over t. Okay, so the sinc function has a width of basically 1 over its own argument. So as t goes to infinity, this thing becomes a delta function in frequency, not in time, which is a delta function that says the only important terms are when omega of the photon is on resonance with this. This is the, okay. So here's where it's always weird, at least the way I have learned, and I struggle with this in how to teach, Fermi's golden rule. The way you do Fourier's golden rule is say, oh, let's take t to infinity, right? And then t goes to infinity, and then this becomes a delta function. But wait a minute. We were doing perturbation theory. In time-dependent perturbation theory, I thought we were talking about the early time. How can we take t to infinity when we just said t was small? Yes?
Separate timescales?
Exactly. It's the separation of timescales. When we're saying, we're looking at times in this problem where t is infinity compared to the correlation time, but especially tiny compared to that. So it's perturbation theory, in time-dependent perturbation theory, say the time is incredibly short compared to the timescale over which the system changes. But it's infinity compared to the time at which the system and the environment are correlated. And that's possible when we have this uncountably infinite number of degrees of freedom. And so really what we're saying is that the time we're looking at to say this infinity is to say that this is much, much bigger than 1 over the bandwidth. Or said another way, the bandwidth of the bath is huge compared to 1 over t, which is the way I drew it. Okay? Remember, this is the correlation time. These are all very confusing, but you have to think about each of these pieces here. So when we're taking t to infinity here, it's only what we're really saying is that the time is huge compared to the correlation time of the bath, which is to say that the bandwidth of the bath is huge compared to 1 over t. Okay? So in that situation, here's where the other rabbit goes into the hat. I can take t to infinity. It's this duality. We're both taking t to 0 in some way and t to infinity. It's 0 compared to this, but infinity compared to that. And the only way we can do both of those things at the same time is if these things, one guy is at infinity plus and the other guy is at infinity minus. That's really the story. Okay, so now with that said, I can do it all. So now I can, let's see, where I want to, which interval do I want to do? Right, I want to do this interval. So let's call zeta of delta is defined to be integral 0 to infinity, e to the minus t prime, e to the minus delta of t minus t prime, or plus t prime minus t. And since this is, I can change variables and call this tau, I can write this as integral from 0 to infinity d tau e to the I omega tau. Right, by delta tau. Yes?
back a little bit.
Yes.
If I turn down the bandwidth of my incident light from going very broadband to very narrowband, does that mean the response to the range of frequencies then increases?
Yeah, well, it's just that I have more, I have a system which will depend on the history more. There will be more oscillatory behavior.
Okay.
So if I have an infinite band source as opposed to a narrow, if I have a narrow band source, I'll get Rabi oscillations. If it's a infinite band source, I'll get irreversible disabsorption with no coherent oscillations.
Okay, sure. I'm just trying to relate it to that line width that you drew of the same.
But that's not the line width of the system. That's about the time scale in which I'm doing the integral.
Okay.
Yes, Nate?
Because our time scale is in this range, does that mean we can't do something like find steady state?
Well, I mean, we can find a steady state. I mean, it's not infinity compared to the dynamics of the system. So we've just taken to infinity compared to the timescale over which the system and the environment still have coherent interactions. So we're saying the timescale over which the system and the environment have coherent interactions is effectively 0 compared to the timescale over which the system changes at all. Here's another example. I usually save this for another time, but here's, let me go to this board over here, which I never use, but what the heck. Okay. Let's say I have a giant lake. A better example of a bath, okay? And, you know, we've gotten rid of pennies. We don't have them anymore. But I have one in my hand. I want to get rid of it. It's hot as hell, okay? And I'm going to throw this penny into the lake. So this thing is at some very hot temperature, okay? Now, I put the penny in the lake. There it is. What's going to happen at this point? It's going to come to equilibrium. This thing is the temperature of the bath, and this is the temperature of the penny, which is much different. This thing, how does it come to equilibrium? Gradually. But like, what is physically happening that allows this penny to come to equilibrium with that?
Cold water hits penny, hot water, it becomes hot, moves away, new cold water.
Exactly, exactly. So there's a molecule of water comes in, bounces off, there's some collision, and then it collides with all these other molecules, and then the next thing of cold water comes in and hits that, and I mean, I can't draw fish. But anyway, you get the point. The way every time, and at this point, this molecule's vibrations are in principle correlated with that vibration, but it was collided with so many other Avogadro's number of molecules, it's gone. The correlation of the water to the system, it equilibrated and came back, the bath of the lake came to equilibrium instantaneously compared to the time scale over which this penny will come to equilibrium with that. So the time scale over which the temperature of the penny changes and eventually comes to steady state. And then there's a time scale over which the molecular vibrations of the ocean or the lake are correlated with the penny. And that time scale is effectively 0 because it happens so quickly, because there's an infinite, 10 to the 23rd degrees of freedom it can quickly spread into. And that's what's happening here. Great. Okay, so, I am so thirsty. That is a problem. All right, so, let's do this integral. So we took t to infinity in the way that we argued was valid, and how do we do this integral? There is no, it doesn't converge, right? So, but what I can do is I can regularize this by putting in a damping function where epsilon is a positive number, and now I'm going to take the limit as epsilon goes to 0 from the positive side. Okay? So I can do that. So this integral is then at this guy it's 0 and at this guy it's 1, so it's minus 1 over I delta minus epsilon limit. Okay, which is the limit as epsilon goes to 0 from the positive side of minus I delta over delta squared plus gamma squared plus epsilon over delta squared plus epsilon squared. Okay. So we can plot the real and imaginary parts of this function as a function of the delta. And what does this function look like? This is Lorentzian. And what does this function look like? This guy is my dispersive line shape. Okay? So this is the real part of zeta, and this is the imaginary part of zeta. The way I've defined the real and imaginary parts here. Okay. So what happens in the limit as epsilon goes to 0? Firstly, what is the height of this thing at at delta equals 0? 1 over epsilon. So what happens, and the width of this is about epsilon. So what happens to this thing as epsilon goes to 0? It becomes a delta function. So another way to get a delta function is the limit of a Lorentzian. So this thing becomes a delta function as epsilon goes to 0. And this thing goes up and then down and then up again. It looks like a 1 over delta, but right near epsilon goes 0, it very quickly goes to 0 again, and then it goes back up again. Okay? So the limit of this thing is minus I to something that's called the Cauchy principal part. Isn't that fancy? I don't know if you ever learned about that. And it turns out that the area under this thing is pi. Under this part. So it's a delta function. The prefactor is the area under the curve, because the delta function integrates to 1. So that's what that limit is. The delta function, we know what that is, but what the heck is the Cauchy principal part? So this is defined such that in the same way that the delta function is only defined inside an integral, the Cauchy principal part is also only defined inside an integral. So the integral of f of x times the principal part dx, say from minus infinity to infinity, is equal to the limit as epsilon goes to 0 from the positive side of minus infinity to 0 f of x over x plus, and that's a 0, to epsilon, plus the integral from plus epsilon to plus infinity f of x over x dx. In other words, it's the integral over everything except the point at the origin, okay? Because that's taken out in that limit. So it gets rid of that singularity. All right, well, with that said, I can now write down the final solution. Oh, shoot. Goodbye.
We'll come out of the.
Maybe. Wait, I'm still flexible enough to do that.
That's
Uh,
okay.
All right, that was fun. All right, let's put it all together. What we have is that the time derivative of that amplitude is the integral from, let's see, I'm gonna write it down here. Integral over all omega times that bath function, which was equal to this. That was the k tilde. And then I have pi times omega at a delta at this. And then I have plus I times Cauchy principal part of 1 over the detuning. Times that. Okay, so now I can do these integrals, and I get the following. This is equal to minus I delta minus gamma over 2 gamma is equal to 2 pi g squared omega g delta eg, and delta, little delta, is equal to the principal part of the integral from 0 to infinity d omega k. Density of states. This is the density of states in that omega. That we said before. I'm not going to put that in there. Density of states times g squared over.
Should that be a full B?
Yeah. Okay.
Oh, that's right.
It's just like bracket.
Okay.
Wait, no, what is that symbol?
Left to the pi.
Yeah, this is private, right?
Wait, well, which symbol that can't you see?
Left to the pi.
This guy?
Top line.
On your top line, you
Top
see a
line.
pi, this is a bracket, right?
Yes. Sorry. Yeah, this guy. I need my LaTeX checker. Okay. So this was what we called zeta. Okay. So when I plug in all of these factors, which we have somewhere or other, this thing is equal to 4/3 over h bar d e g squared omega e g over c cubed.
Just the gamma or
The whole, this whole thing. Okay, so let's interpret this. What do we see? What we see is that when we did the Born-Markov approximation, we ended up with a differential equation just for the excited state, which has this form. What do the two terms represent? This tells me that the solution to the Schrödinger equation, after all is said and done, was That's a solution to that differential equation. What is the probability to be in the excited state as a function of time, given that solution?
That's square.
Exactly. So the probability to be in the excited state with no photons in the field is the magnitude of this square, which is what?
Exponential decay.
Yep.
Over.
E to the minus gamma, it decays at that rate. And this was 1. Okay, so we get exponential decay, and the rate of exponential decay is what we found. And in fact, this is just Fermi's golden rule. It's another form of it. Fermi's golden rule involves the square of the matrix element times the density of states. It's here again. So we did Fermi's golden rule, really, but we did a little more because we allowed it not just to change linearly with time, we did the Wigner-Weizkopf thing and we got exponential. Okay, so this, we've long said there is some spontaneous emission rate gamma. This is it. This is the spontaneous emission rate. What does it depend on? It depends on, remember DEG here is the matrix element of the dipole operator between the excited and ground state. So it depends on the strength of the dipole matrix element. It also depends on omega, the rate of decay, it's not the rate of decay at all. The frequency, remember omega EG is the Bohr frequency, it's the resonance frequency. Okay, so a state that has a higher energy difference and therefore a bigger omega decays much faster than one that where the energy levels are slow. So if I had 2 energy levels, say, if I think about a hydrogen-like atom, where I have, the ground state, and then the first excited state, and then the second excited state, and the third, and and it goes all the way up. That if I'm in the first excited state, I'm going to decay much faster to that than if I start here and decay to a nearby level. This might be 100 terahertz, this might be a gigahertz. Yeah?
Wasn't there something we were talking about, was it Rydberg states or something like that? They take a long time?
That's what I did, and that's exactly what I was just saying. So if I look at this state, let's say this is the first excited state. So, here's the ground state of hydrogen, 1s. Here's an excited state, 2p. That state has, a very fast decay. Whereas if I look at 2 states here, n equals 50. Well, first of all, does this n equals 50 decay to n equals 1? It could. That would say, because it has a big frequency, but it has a tiny matrix element. Tiny, because the overlap of that wave function with the ground state is almost nothing. So the matrix element that's dominated is a nearby level, maybe 49, but then it's slow because that energy difference is small, and because that energy difference is small, the frequency is small, and thus it decays very slowly. So they have very long lifetimes, the states up there at high principal quantum numbers. Okay. All right, so this is the spontaneous emission rate. What is little delta? What does this represent?
Capacity for coherence.
Well, it is definitely something more oscillatory, so it's true, there's something kind of coherent-y about it, I agree. How should I interpret what that little delta is? Remember that we're in the interaction picture. In the interaction picture, we've taken the free evolution out of the state, and we've put it into the opposite. Let's go back to the Schrodinger picture. In the Schrodinger picture, the state, I have to put the free evolution back into the system. Okay? What does that do? Well, so if in the free evolution, this thing would have evolved according to this time dependence. When I then include the interactions, now I have these two terms, the decay, but how should I now interpret delta? Well, it's a shift in the energy. It's the perturbation, the energy is shifted due to the interaction. We don't only get, when I start in the excited state, due to the coupling to the vacuum, I know I not only get a decay, but I get an energy level shift. Light shift. Now it's not the light shift, it's the Lamb shift. It's the shift due to the vacuum. When you couple a system to a, if you have an interaction Hamiltonian, that perturbs the energy levels, okay? So this we recognize from second order perturbation theory as the square of the matrix element divided by the energy denominator. This is, in second order perturbation theory, what we call the energy level. Now this integral is not well behaved, and Willis Lamb did it right, doing the full, because to get it right, you really, the non-resonant terms that you remember, we have to go beyond the rotating wave approximation to get the Lamb shift right. But this is the Lamb shift. It's a contribution to Lamb. It's the fact that when you couple a system to another system, not only do you cause population to move around, you also shift the energy levels around. Very nice. All right. Yes?
Would it be wrong to say that lambda's coupling to the vacuum versus the decay rate is coupling to the environment? Are those like two sides of the same coin, or am I imagining that?
The vacuum is the environment. What else is the environment?
Path.
But what is the path? What does it consist of physically?
EM waves.
Right, which is, there's nothing there. I'm not, there are no waves around. So the only thing in this case is the vacuum. So it's the fact that even in the absence of any photons, the atom is still coupled to the quantum field. There is still a coupling to the quantum field. Now it's actually an interesting point where let's think about the coupling. Let's suppose at t equals 0, there are thermal photons. Near resonance. Someone else have a question that I missed? I'm sorry. I didn't saw that. Okay. So this is the situation where now, at whatever temperature we're at, there's some thermal photons with a certain black body spectrum, right? So in this situation, I have, we know at that frequency, there's a mean number of photons given by Planck's formula, right? So there's some thermal photons around. If we are at room temperature, then KT is about a 40th of an electron volt. So there's not many thermal photons. There's plenty of gigahertz photons around, so I would have to worry about this, say, for those Rydberg levels that are nearby, and think about that effect at this point, okay? So if I wanted to, I can try to calculate the rate. So what will happen in that case? So now I have, I'll call this some E1 and some two excited states. This one's at a lower energy. This guy can spontaneously emit according to that, but it can also have what we call stimulated emission, okay? So the stimulated emission we think about as being induced by the black body photons. The spontaneous emission, we say, is like stimulated emission by the vacuum, okay? Now this is a language that we also often use. I'll maybe try to say a few words about this. We'll finish this up in our last lecture. This can cause a great degree of confusion. The idea that spontaneous emission is stimulated by the vacuum and the role of vacuum fluctuations in spontaneous emission. But let me see where this argument came from. The idea of stimulated emission versus spontaneous emission came from Einstein. So Einstein was trying to understand how a matter came into equilibrium with thermal bath, where the thermal bath were thermal photons. I have a black body, I have photons in a cavity, say, at a certain temperature, and eventually I should get a Boltzmann distribution with a certain population in the excited state compared to the ground state that depends on the temperature, right? So this is the thermal photons at that temperature. How does that happen? What Einstein said is there has to be these two processes, the only way, just solving it just from the point of view of rate equations, okay? What he said is that there's a rate of spontaneous emission which he called the A coefficient. We call it, sometimes called the Einstein A coefficient, which we now call gamma. And there's a rate of stimulated emission. Which he said was proportional to the energy density per unit frequency in the field. So U of omega is equal to the thermal number of photons times the density of states as the number of modes per unit frequency times h bar omega over the volume. Okay, that's the energy density, right? I have, each photon has this per unit volume, and he solved for that, okay? And what we're going to do it next time using Fermi's golden rule, and what we find is that V times for thermal photon is equal to this. We'll solve that next time. But how does that compare to the Einstein A coefficient for gamma? It's the same thing, except n is 1. So this gives us often this interpretation that I should think about there's a vacuum photon that is somehow stimulating the system to emit. That's a kind of standard laser physics-y picture, but it's not physically correct. It's numerology, but it's not physically correct. Why isn't it physically correct? Number one thing, there are no vacuum photons. There is no photon. Now you could say, and it's physically music, well, it's induced by vacuum fluctuations. The uncertainty is somehow jiggling the system, and somehow that is stimulating it to emit. And there is some validity to that, but it misses an important picture. And what we're going to talk about next time is the story of radiation reaction. So in my last extra 1 minute that I'm going to take, because I always end at 10:47, I want to ask you the following question. Suppose I had a charge, say it's a negative charge, doesn't really matter, on a spring. It's got some mass. It's bound on a spring. And it has no friction. There's no air friction. This spring is ideal theory spring. It's got no friction at all, okay? And I pluck this spring and I let it go. What's gonna happen? Let's say I displace it by some amount, A, okay? And I wanna know what is the position of this thing as a function of time. What will happen to this thing? It will oscillate, okay? Will it oscillate? It has no friction. Does it oscillate forever with the equal amplitude? It has no friction? No, why not? It radiates. In fact, what happens is you get exponential decay. Why does it exponentially decay? Is what I already said. Because when this charge is oscillating, it's accelerating. And accelerating charges radiate dipole radiation. And so it radiates a dipole radiation pattern. Electromagnetic waves go away. Those electromagnetic waves carry energy, and therefore the beam damps. That's spontaneous decay. To what degree can I understand spontaneous emission in an atom as radiation reaction, and to what degree is it really due to the vacuum? That was an interesting mystery of the 1970s, and we'll talk about that as our last lecture. All right, 1:48.